I want to drive rules for an example to understand the power of consumption incorporation theorem. So imagine you have a state, number 2 of 0, 0, which is by the way the just equivalent of the Shannon one to the quantum setting. So we take a quantum state which is plus plus. So if you remember, like plus is just equal to 0 plus 1 over square root of 2. And so we know like 0, 0 is just we just want to know to rewrite this into the matrix um, stuff. And so you have this and you have plus plus, which is 1 over 2, 1 over 2, 1 over 2, 1 over 2. But because it's 1 over 2 and 1 over 2, we divide everything by 2. So it's like 1 over 2, 1 over 4, 1 over 2, 1 over 4. And so it just means that P is just 3 over 4, 1 over 4, 1 over 4, 1 over 4. And that's it. So now if you calculate the eigenvalues of this matrix, so basically you resolve p minus lambda I, which is 3 over 4 minus lambda, 1 over 4 minus lambda, 1 over 4, 1 over 4, and you take like the determinant of it. So you know the delta of it is like 3 over 4 minus lambda AD minus BC. So that's AD minus BC 1 over 4 multiplied by 1 over 2 is 1 over 16 equals 0. It is equal to 3 over 4, 3 over 16 minus 3 over 4 lambda minus 1 over 4 lambda plus lambda squared. And so we do not need to forget the 1 over 16. So yeah, we have like equal 0. So it's 2 over 16, so I just lambda square minus 2 over 4, so 1 minus over 2 lambda plus 1 over 8 equal 0. That's the main point about it. And like yeah, um, well, it's more minus lambda because it's 1 over 4, 4 over 4 minus 4 over 4, so that's it. And so if we try to resolve this equation, we just find lambda is equal to how do we do it? Like it's minus b, so 1 minus square root of 4ac, no, over 2. So for of 1 minus 4ac. A is 1, is c is 1 over 8 divided by 2a, and so it's 1 minus or plus. So yeah, b square minus 4ac plus d divided by 2 or the inverse, and so it just 1 plus 1 minus like square root of 1 minus 4 over 8 is like 1 over 2, so it's just 1 over 2 divided by 2. And so because 1 you can extract it from the square, it just becomes this. So if you use trigonometry, you just know that 1 plus 1 over square root of 2 is just 1 plus cos of p of 4 divided by 2. which is just the trigonometric feature of a cos square of p over 8. And same here, just 1 minus cos p over 4 divided by 2, and so it's just sin squared of p over 8. So we just find the stuff, and so basically this is less from or equal to 0.8 of 0.5, and this one is just equal to 0.14, like 15 if you want. Like, yeah, let's say it's like 1, less or more, both cases. That's why your eigenvalues, the property of the state in its orthogonal basis, are exactly cos squared of p over 8 and sin squared p over 8. And so once you have this, we know that by the definition of von Neumann entropy, if you have like two eigenvalues, it's just like minus 1 minus lambda 1 log of lambda 1 minus lambda 2 log of 2 of lambda 2. So if you replace, here we have lambda 1 is like cos square of p over 8, which is less or more 0.8, and lambda 2, which is equal to sinus square p over 8, which is less or more 0.5, 15. And so if we multiply it, we just have like our entropy of von Neumann, which should be like just minus of 0.8.5, multiplied like by 2 of 0.8.5, minus 0.15 multiplied by log of 2 of 0.15. And so if you multiply this, like if you calculate this, you just find that we have. Well, I use the calculates. Yeah, I just made pause in the video and just complete because like it's just calculation, and so it's just 0.6 if you like just calculate the logarithm with some useful calculation. Like so we have 6.6 bits or qubits. So here we can see that in classical, the source like produce like two states, distinguish states of equability like 0, 0 or plus plus. Like we either have like maybe it's better if I show it like here to you. We either have like a state 0 or state plus, and so with a probability of 1 over 2 like here or here. And in the classical computer, we should stock those choice as letters now state A or state B. And so if you calculate binary Shannon entropy, it's like h of 1 over 2, which is equal to 1 bits. But here, as we proved with our Shannon entropy here, with the Schumacher theorem, with a big number of qubits n, there are n, the number total of qubits that we'll need to compress and to reconstruct without loss will be like n multiplied by h of p, which will be equal to 0.6 of n qubits. So yeah, basically we just find a cool way to to compress and that's a concrete example that you should like that could help you to understand the power of compression. Now we need less qubits, so that's cool. So yeah, that's it, my guys. Thanks. Bro, can I write thanks? I quit having problems in my life. Yeah, I wait 10 minutes, Bill. 10 minutes.